Hello everyone. Hope I'm audible. Okay, we have some attendees. We can start. Okay. So welcome to week six discussion session where I will be discussing the previous year's week six assignments, and then we can also look into if anyone has any confusion. We can look into that also. So let's begin. Okay. So the first question is find X minimizing the normalized delay for the two-stage circuit where C is unit and NMOS capacitance. Okay, so we have been given a circuit from the discussions and what Sir has taught. It is clear what if these are the four inputs A, B, C, and D. It is basically AB bar, this is CD bar, and this should be AB bar whole into CD bar. So if you solve it, you will get AB plus CD. It is implementing this logic. Okay, so let's look into all the capacitances that are present here. So it's clearly it would be X, it is 100C, it would be 20, this would be 20, okay. So now let's look into the individual parasitic delay and logical efforts of each of this stage. So here what will be the P1, what will be the G1, what will be the P1 for this stage, what will be the G1 for this stage. Okay, now clearly these are NAND gates, right? So NAND gates is like this. You will have PMOSes in parallel and NMOSes in series. Okay, so the net capacitance is connected here would be sizing would be 2 2, and this would be 2 2. So here it would be 4. So my parasitic delay would be nothing but here it would be 2 from here, 2 from here, and 2 from here. So it would be 6. So my parasitic delay would be 6 C by the capacitance of an unit inverter, which is 3C. So it will come as so it will come as 2. Similarly, it's an AND gate, so similarly 6C by 3C should be 2, and my logical efforts would be this 4 divided by capacitance of an unit inverter, so 4 by 3. Similarly, G2 would be 4C by 3C to 4 by 3. Now what will be the path electrical effort? It will be the output capacitance by input capacitance. See here, all the inputs, all the 4 inputs are identical, so I can take any of the path to be the critical path. So let me consider A to be the critical path. So here output capacitance is 100C, input capacitance is 20C. So my path electrical effort would be 100C divided by 20C. So basically 5. Now we know capital F would be nothing but G into H, where G1 is product of all the individual logical efforts. So here there are 2 stages, so it will be G1 G2 into capital H. So G1 is how much? G1 is 4 by 3, G2 is again 4 by 3, and H is 5. Okay, so it would be okay, so let me put it in this form only, and we know this small f would be nothing but f to the power 1 by n, where n is the number of stages. here, as there are two stages present, so n is 2, so it would be 4 by 3 square into 5 to the power half, so 4 by 3 root 5, f is coming. Okay, so how much it is? It is coming as, let me calculate, 4 by 3 root 5, it's nothing but 2.981. Okay, then okay, so the individual stage effort is coming as 2.981 for optimal delay. Okay, so now I can easily find the value of x, because here if I try to find h1 here, h1 would be nothing but how much, x1 by 20, and here h2 would be nothing but 100 by x. Okay, so say for stage 2, okay, this f would be nothing but g2 into h2, and g2 I know it is 4 by 3, and h2 would be 100 by x, and f is calculated to be how much, it is 2.981. so simply 2.981 equals to 4 into 100 by 3 x, so x is nothing but 400 by 3 into 2.981, so around 39. So how much it will come? It will come at around so it is coming as, x is coming as 44.72. so do we have 41.72? yes, we have 41.72. so this is the correct answer. Clear? You just okay, you just need to find the total path effort, and then you have to find the optimal stage effort. Then you can simply use gh, f equals to gh, to find the value, the size for optimal delay. Okay, so second question is, what is the minimum normalized delay for the design stated in question 1? Now they are asking the value of the delay. So we know delay is, what is the net delay? It is sum of individual parasitic delays plus n into f to the power 1 by n, that is n into small f. So what was p1 and p2? It was 2 plus 2. So for two stages it will be 2 plus 2, and n is also 2, and f is how much? F is 2.981. so basically it will be 2 into 1 plus 2.981, so around 2, 3, 5, around 10 it will come. How much it is coming? 2 9.962. so this is the correct answer. Okay, hope that's clear. Okay, let's move forward. Question number 3. So select the correct option about the following statements. Compound gate design offers less area and decrease in delay when compared to multi-stage design. So always remember, as a rule of thumb, you can say that what does compound gates do and what does multi-stage design do. These multi-stage designs generally like you will be having multiple stages of circuits, right? So this allows you to optimize the circuit for lower delay. Okay, so multi-stage circuits always leads to low delay, because you can add more number of inverters and find the optimum number of stages, and then you can find the optimum size of each gate, so it will give you low delay. Whereas these compound gate designs, they are generally used when area is is a dominating factor or a major factor. Okay, because you can implement complex logics in a single stage, or if you take the inverter, then within two stages. Okay, so compound gates are used when area is a factor. So compound gates always lead to low area. And you must have seen by the examples that sir has given that the delays, and when you compare the delays and the areas, the net delay was lower in case of multi-stage gates and multi-stage designs, and for compound gate design, the total area came to be lower. Okay, so let's look into the four statements that has been given to us. The first statement is compound gate design offers less area, which is correct, and decrease in delay, which is false, because we have seen multi-stage gate design gives us lower delay. So first one is false. Second one, compound gate design offers less area, which is true, but increase in delay, which is also true when compared to multi-stage design. So second one is true. Third, compound gate design offers more area, which is false, but increase in delay, which is true. So it is also false. And fourth statement is compound gate design offers more area, which is false, but decrease in delay, which is true when compared to multi-stage design. So it is also false. So my correct sequence would be false, true, false, false. So this is the correct answer. False, true, false, false. Okay. Hope that's clear. Okay, let's move forward. Question number 4. Okay, what is the length of the equivalent transistor if we consider width of equivalent transistor as 3W for the following circuit? Okay, now I can do it in easy way and I can do it in a complex way. Let's first do in the easy way, and then we'll look at the complex method also. Okay, so first of all, you can see for this one W is given as 2 LSL, here W is given as 4 LSL. And what has been mentioned, what is the length of the equivalent transistor if we consider width of the equivalent transistor as width of the new transistor has been given as 3W, and I have to find the length. Okay, so let us consider it as XL. So we know this value of this X is going to, we can directly get it from getting the ratio of this transistor to this transistor plus ratio of this transistor to this this transistor again. So X can be simply calculated by 1 by 2W divided by 3W plus for this one 4W divided by 3W. Okay, so it will be 6 plus 4, it will be 3. Sorry, it will be how much? It will be simply, sorry, I have written the formula wrong. It would be 1 by 2W by 3W plus 1 by 4W by 3W. Okay, now it's correct. So it will be 3 by 2 plus 3 by 4, 6 plus 3 by 4. So it's basically 9 by 4. Okay, answer is 9 by 4L. Therefore L dash is 9 by 4 into L. Okay, so this was the easy method. Now why so what is the physics behind it? Let's look into details. So basically what has been asked, that we find a transistor which leads to similar amount of current. Okay, so okay, it will be 3W and XL. So my current should be same in both the cases. Okay, and let me call it A, B and C, and let me call this voltage as Vx. So from our previous discussions that we did in the initial classes, you remember that if it was an inverter, the pull down network of an inverter, this transistor should have been in which state? It should be in saturation region, and this transistor should be in linear region. Similarly, this transistor should be in, if I remember correctly, it is in saturation region. Okay, this transistor. So as I need equal amounts of current, then I should equate, like I'll be writing the current equation for these three transistors, and I'll be equating them, and I'll be getting the I'm having two variables here. One is Vx, another is size x. So from I have two equations and two variables. I can simply find the value of x then. Okay, let's look into it. So first of all, the first equation, let me write it for this transistor. It's in saturation conditions region. So it would be beta by 2 W is 2 by 1 by L VDD minus Vx minus Vt square. Let me write VDD minus VDD minus Vt as VDT. So it would be beta VDT minus Vx square. Similarly, the current through this one, which is in linear region, would be beta into 4 by 1. Okay. VDD minus Vt minus Vx by 2 to Vx. Okay, fine. Now the current through this the final transistor that we are designing would be again in saturation. So beta by 2, 3W, it is 3W and x, so 3 by x VDD minus again VDD minus Vt, no x, so VDD minus Vt whole square, which is VDT. So 3 by 2 beta x VDT square. So this is my equation 1, this is my equation 2, this is my equation 3. For the two variables are this x and this Vx. Okay, so let's solve for let's solve for x first. For x, I'll be taking Ia Vx. Okay, let me first use equation 1 and 3. Okay, use here. One and 3 equals to IC. So beta by beta VDT minus Vx square equals to 3 by 2 beta by x VDD square. Beta cancel, so x should be equals to 3 by 2 VDT square by VDT minus Vx square. This is equation number 4. Okay. From equation, now let me take which two x. Now let me equate 1 and 2. from 1 and 2, IA equals to IB implies Vx square is to beta 4 VDD into Vx. Okay, so beta will cancel. Vx square equals to Vx minus 4 to Vx square. Hope I have not made any calculation mistake. I should get the answer correctly. Let me check. Okay, so it would be let me see what comes. PDT square minus 6 VDT plus 3 Vx square equals to 0. Now if I solve for this Vx, I'll get 3Vx square plus VDT square. Okay, fine. So Vx would be minus b, that is 6 plus minus b square minus 4 into a into c. C is how much? VDT square by twice a. 6 plus minus sorry, it will be 36 VDT square. Okay, so 36 minus 12 is 20. How much? Root 24. 24 VDT by 6. 4 into 6, it will be 12. 4 into 6. 2 root. Yes. I don't get you. Everyone is seeing a mirror view? Can anyone confirm? Anyone? Netra or Uthra or Harish, Vinay? Everyone is seeing a mirror view? Okay, it should not be, because I'm just simply presenting the screen. It might happen that you can simply rejoin the meeting. I hope then it would be, the problem would be solved. Sure, sure. Okay. Okay, fine. Okay, so this is something, it is coming. PDT. So okay, I think I have done some mistake here. Let me check once. PDT Vx should be there. So 6 plus minus 4, 4 to root 6 by 6. Okay, it is coming like this. And if I solve it, how much is coming? 6 minus it is coming as 0.18. Okay. Okay. VDT. Therefore, X should be now equals to from here X is 3/2 VDT square divided by VDT minus Vx whole square. So 3/2 VDT square VDT minus 0.1835 VDT square. Okay, so 2.286 it is coming, and 2.286 is the answer. That is the value of X, and initially how much we have got? 9/4. So 9/4 was, see, now we are getting 2.286 and initially we got 9/4, which is equals to 2.25. so you can see we are getting a close answer, right? So you can either do this analysis from where we are getting the result, or you can simply use this formula and use this formula and get the result 9/4. Okay, I think I have done it to show you the mathematics of how we are actually getting it. That's all. You can simply use this formula, the short one. Okay. Okay, then let's move forward. Now, question number 5. Okay, the next question is, for a short channel NMOS transistor of width XW and length 4L/3, what should be X to get the current same as benchmark inverter's current with width W and length L for benchmark inverter? Okay, let's look into it. Question number 5. Okay, so it has been given that the transistor is short channel with width XW and length 4L/3, and it has been said that what should be the value of X so that I get the same current as benchmark inverter's current. Okay, and I'm assuming that my benchmark inverter is also a short channel NMOS transistor. Okay, so basically the current for this one would be, it is short channel, I am assuming that this device is in velocity saturation. Okay, not normal saturation but velocity saturation, because it's a short channel device. So generally for short channel devices, velocity saturation kicks in before it can enter normal saturation region. So my current would be, current for this transistor is, we know the net W, which is XW here, into COX into Vsat, saturation velocity, into VGS minus VT whole square divided by VGS minus VT plus EC into the new length. So EC into L is basically EC into new length is 4 by 3 L. So it would be EC into L will be VC critical velocity plus 4 by so not plus VC into 4 by 3. Okay, and my benchmark transistor current would be benchmark transistor, that is width is W and length is L. It would be net width W into COX into Vsat into VGS minus VT square divided by VGS minus VT plus VC EC into L, that is VC into 1 here. Okay, and it has been said that we have to find the X so that these two currents are equal. So my IXW 4L by 3 should be equals to IWL, implies XW COX Vsat VGS minus VT whole square divided by VGS minus VT plus critical voltage by 4 by 3 is equals to W COX Vsat VGS minus VT whole square divided by VGS minus VT plus V critical. Okay, so you can see W COX Vsat will cancel out each other, this term will also cancel out each other. What I will get is X equals to VGS minus VT plus 4 by 3 VC divided by VGS minus VT plus VC. Okay, and from here we have been given these values. So S is taken to be grounded, so VGS is VG, that is 1 volt, minus VT is 0.3 volt plus 4 by 3, and VC is given as 1.04 volt divided by VGS is again 1 minus 0.3 plus VC is 1.04. So let us find how much it is coming. It is coming as 1 minus 0.3 plus 4 divided by 3 into 0.04, okay, divided by 1 minus 3 plus 0.0. It is coming as 1.199. Okay, anything near it, the first option 1.2 is near it, so first option is the correct answer. Is it clear? Any confusion? Okay, okay, fine. Then let's move forward. Question number 6 is, what is the average logical effort of an inverter skewed in the ratio PMOS with 2 and MOS with is 0.5? Interesting question. See, the skewed inverter that has been given to us has sizing like this. It is given as 2, it is given as 0.5. Let us quickly write the internal capacitance value. Sorry, input capacitance value. It will be 2 plus 0.5, 2.5. Now to find the average logical effort, we have to find the pull-up logical effort and pull-down logical effort. So let us quickly write, draw the pull-up logical effort benchmarking circuit. Okay, so for pull-up it would be, as it is 2, so it will remain 2 only. The pull-up one would be as it is 2, it would be 2, and NMOS is generally half of it, so it would be 1. So here the capacitance is coming as 3C. Therefore G pull up would be how much? It would be 2.5 divided by 3, so 5 by 6 basically. And for pull down network, as this is 0.5, my pull down will have as it is 0.5, my pull down will have 0.5, and PMOS would be double the NMOS size, so it would be 1. So my G pull down would be nothing but, so the capacitance connected here is how much? It is 1 plus 0.5, 1.5. So G pull down would be pull down would be how much? It would be 2.5 divided by 1.5, so it is 5 by 3. Therefore G average would be average of G pull up plus G pull down, so 5 by 6 plus 5 by 3 whole divided by 2, so 5 plus 10 divided by 12, 15 by 12, which will come as 5 by 4. Answer is 5 by 4. Hope that's clear to all. Generally finding this logical effort and all for skewed circuits are relatively easy compared to other things. You just need to ensure you have to just draw the reference circuit, reference inverter, ensuring that the current in both the reference inverter and your circuit for pull up logic or pull down logic that you are considering are equal. Okay, like for simplicity I said here that their sizes should be equal, but no, actually their current should be equal. That's why when you go to pseudo NMOS logic, you will see that though like my sizes might be equal, but the net current, as there will be a static current, so due to this my net current would differ. So we have to ensure not the sizes but the net static current, the net current flowing through them should be equal between my, that is between my pull up or pull down network and my reference CMOS inverter. Okay, you can find it in this way. Okay, it came in the below. Let us look into it. Question number 7. Okay, select the correct option. The best PN ratio for an inverter is root 3 by 1. Now let us look into it. We know if we know the P by N ratio for an unskewed inverter, we can find the P by N ratio for the best case in terms of delay by simply using this formula. The formula is P by N of unskewed is equals to P by N of best. So if you want to find the best P by N ratio, just take the square root of P by N of unskewed inverter. Okay, so what are the three circuits that have been given to us? Inverter, NAND and NOR. Then let us find the unskewed P by N ratio, then let us find the best case. Okay, for inverter first, inverter is basically this circuit. So what will be the P and N? It's basically 2 and 1. So for best case, so for unskewed case, for the best case, unskewed case, P by N is 2:1. So best case it would be root 2:1. Okay, second is given as how much? A simple NAND gate. Okay, Let me try two input NAND. Sorry. So what will be the sizes? It will be 2, 2, 2 and 2. So for unskewed case, my P by N would be, as they are similar, so 2 by 2 equals to 1 is to 1. So for my best case also, it would be root under 1 is to 1, that is 1 is to 1. So for NAND gate, for NAND architecture or NAND gate in general, my unskewed architecture gives the best P by best is the best case for my delay consideration. Okay, and third is a NOR gate. Okay, so what will be the sizes? It will be 1 1 and here 4 and 4. Okay, so what is the P by N here? It is 4 by 1, so 4 is to 1. So for the best case, it would be root under 4 by 1, so 2 is to 1. Okay, so now let's look into the three statements that has been given. The first statement is the best P by N ratio for an inverter is a ratio of root under 3 by 1. So we have found that for an inverter it is root under 2 by 1 and not root under 3 by 1. So first one is false. Correct? Okay. The second statement is the best P by N ratio for a NAND gate is an unskew of 1 is to 1. So what we have seen for a NAND gate, the best case comes for that of an unskewed inverter and it's equals to 1 is to 1. So the second statement is true. Correct? Third statement is the best P by N ratio for a NOR gate is a low skew of 2 is to 1. What we have seen for a NOR gate, the best P by N, and yes, one more thing, it would be a low skew inverter. Okay, so the best P by N ratio is coming as 2 is to 1. So it's correct, true. So the correct sequence is false, true, true. It is the correct answer. Clear, everyone? Yes. Okay. See, this one is not a low skewed one. So when we'll be making 2 is to 1 circuit, like this is the standard one, right? So my net circuit would be how much? P by N ratio is 2 is to 1. So what was low skew? If I remember, what was low skew? Low skew was we are what we are doing. We were reducing the strength of the PMOS stack, right? For low skew. So just give me a minute. High skew was when high PMOS strength was kept same and NMOS strength was reduced, and low skew was the lower stack, the pull down stack has been kept same and the PMOS stack has been reduced. So yes, this would be my what it will be? It will be low skewed, correct? And from intuition also you can see in this one which are the which, if I name them M1, M2, M3 and M4, which transistors do you think has the highest contribution in capacitance, pull down or pull up, and which out of these four transistors? Yes, so these two, right? M1 and M2, because they are having the highest amount of sizes. So if I can reduce their size to some extent, then it's obvious my net delay would come down. Maybe during charging, during the pull up operation, the net current would also reduce, and it will take more amount of time to charge, so my pull up logical effort would increase. But uh, while uh, while doing this pulling down operation, that is while discharging the capacitor, as it will see a net capacitance, the net capacitance that would be encountered would be low at the output, so my pull down operation would be, the operation would be faster, right? So my pull down logical effort would come down. So this is the idea behind the low skewed. And when it is used in certain circuits, generally high skew and low skewed are used in many cases, but one of them is in memory applications. Because if you I don't know whether you know about it or not, when you want to, like, data are stored in memories, right, right, 2D stacks or 3D stacks memory. So we need to access them. For accessing, we have something called bit line and source line. Okay, so there are certain operations where bit line voltage needs to be, we need the this transition to be very fast, low to high, but this high to low transition might be slow, or vice versa. Okay, so in such kind of operation we use these high skew and low skew circuits. Like here you are talking about. Okay, root 2 is to 1. So yes, you are what you will be doing is you will be making it like PMOS would be root 2 1.414, and NMOS would be 1, so it would be also low skewed, correct? Okay, fine, let's move forward. Question number 8. Find the size of a k input pseudo NMOS NOR gate whose inputs are driven by 1 unit inverter each. The output of the NOR gate is connected to a capacitor of 18C, where C is unit NMOS capacitance. Okay, so let's draw this circuit. So there are basically k unit inverters driving a k input NOR gate, right? So how many such inputs are there? K. It's a NOR gate. It has been connected to a capacitor of 18C. 18C. Okay. I need to find the size of this, and it is an pseudo NMOS NOR. Pseudo NMOS NOR of let me consider the size to be X. Okay, so let's quickly find out the logical effort and electrical effort, and the parasitic delay of each state. So it's an unit inverter. So for first stage, my logical effort would be 1 and parasitic effort would be 1. Here it's how much? It's 8 by 9, if you remember, or I can find it also for you. Okay, I'll be finding it for you. P2 is how much? For k stages it is 4 by 9, 2k plus 1, and each should be basically, you can see here the capacitance connected is X, so it should be X, and here each one, H2 would be H by X. Here this is also H, which is 18C by XC. So it's 18 by x. Now how I have got this number 8 by 9? If you look into this is my k input pseudo NOR gate, right? So what were the sizes? 2 by 3 and 4 by 3. How we are getting that? I hope you have seen the lectures. So will be for pseudo and NMOS logic we are getting such kind of sizes 2 by 3 and 4 by 3. Basically what we are doing, we have to ensure that this charging and discharging current are equal, because this output capacitance that we will be seeing, there will be two currents. One will be this discharging current, and another will be this continuous charging through this PMOS, because PMOS will always be on. So the net current here will be the difference of these two current. So we have to increase the size of this NMOS pull downs, the size of this NMOS in the pull down strand. Initially generally what do you use? We use 1, but here as some current is also like 1 by 3 amount of current, because this is 2 by 3, so 1 by 3 amount of current is also coming, charging the capacitor continuously, so we need a higher amount of current, so we use the width to be 4 by 3. And you can simply, even you can take the size to be alpha and beta times alpha, and you can simply write the equation and you can solve to find these values 2 by 3 and 4 by 3. Okay. Okay, so okay, logical effort we are talking about. So the logical effort here will be how much? It will be 2 by 3 plus 4 by 3 divided by that of an unit inverter. Sorry, 2 by 3 will not come. Sorry. Let me find for pull-up step. As no input is connected here, inputs are connected here, it would be 4 by 3 divided by, I'll be drawing the unit for this. I'll be drawing the reference transistor, it would, inverter, it would be, the sizes would be how much? As it is 2 by 3, I'll be taking it 2 by 3, and NMOS would be half of that, so 1 by 3. Okay, so 4 by 3 plus 2 by 3 plus 1 by 3. This is pull up, so it would be 4 by 3. And for pull down is little tricky. And why it is tricky? Because I cannot simply consider the size of it, because some current is also charging this capacitor while this transistor are trying to discharge it. So what I will be do, I have to find the net current, and the current through this is I by 3. If I consider, this would be 4 I by 3. So the current actually is 4 by 3 I minus I by 3. So it is actually 3 by 3, that is I. Okay, so I have to use my old fashioned reference CMOS inverter, because this is giving me the current of I, this inverter. Okay, so my G pull down would be become how much? It would become 4 by 3 divided by capacitance of this one. Here it is 3C, 3, right? So here it was how much? Here it was 2 by 3 plus 1 by 3 is 1. So it will be 4 by 9. And the average would be and G average would be 4 by 3 plus 4 by 9 divided by 2. Solve it, it will come 8 by 9. 12, 16, 16 by 18. So 8 by 9. So this is how I'm getting this 8 by 9 here. Okay, fine. So now, okay, so now we know the path effort would be capital F. This capital F would be how much? G into H, and G is nothing but I, G, I, H, I, and I it would be actually G1 into G2, because there are only two stages here. One stage this one, another stage this one, and into HI it would be capital H. G1 is 1 because it's an inverter, and G2 is how much? I just calculated G2 to be 8 by 9, and H is 18C by 1C. Okay, so small f would be f to the power 1 by n. N is here, equals to 2 here. Therefore, f would be this is 2, 16, root under 16. Okay, equals to root under 16. 8 into 2, 16. Therefore, f equals to 4. Correct? Now I know f equals to 4, and from this one, if I consider a single inverter here, so my f is equals to G1 into H1. What was G1 for inverter? It was 1. And what was H1? If you remember, it was x by 1, because and capacitance of x has been connected here. Okay, so it would be x by 1. Therefore, f would be equals to x. Therefore, x would be equals to f, which is equals to 4. Therefore, the size of this pseudo NMOS inverter would be equals to 4. Clear? 4 is the correct answer. Is it clear to everyone? If you need a minute to recapitulate everything, just take a moment and go through it again. If you find any confusion, please let me know. I hope it's clear to everyone, right? So we can move forward. Okay, let's move forward. The next question is, find the delay in the above equation, question number 8, for a 3-input NOR gate. Fine. So we'll be finding the delay. There is no problem in what we have been given. We have been given the number of inputs. Let us call this as k, is given now as 3. Okay, k is given as 3. So we know delay would be equal to okay. So delay would be equals to the average parasitic delay of this NOR gate, this average parasitic delay, plus delay of these inverters. Like if I draw the critical path, as all the inputs are equal, say the critical path would be something like this. Okay, so I'll encounter one inverter and this NOR gate. So P average parasitic delay of average of the NOR gate plus parasitic of an inverter, okay, plus n into f to the power 1 by n. Okay, or f to the power 1 by n is simply this small f. Okay, so we know this is the value from the lecture. Sir has directly provided us with this value. It would be 4 by n, 2k plus 1. And if you solve this, if you want, you can find it for this one also. It will be simple. Okay, plus P inverter is 1, we know that, and n is 2 here. F is how much? F is 4. Sorry, f is 4. So what will be my net delay? And k is given as 3. So 4 by n, 2 into 3 plus 1 plus 9, 4 into 2, 8 plus 1, 9. So it would be 2 into 3 is 6, okay, 6, 7. So 28 by 9 plus 9. Okay, how much it is coming? It is coming as 12.11. 12 sorry 8 plus 4 plus 28.9, 3.11 plus 9, so 12.11. Clear, everyone? Any confusion? Anyone? Please let me know. I hope I am audible, right? Okay. Okay, fine. So let me move forward to the last question of the day. Okay. Find the average logical effort of a ganged CMOS NOR gate which has PMOS size 2 by 3 and MOS size of 4 by 3 and whose output is connected to 4C, where C is unit NMOS capacitance. Okay, fine. So let me first draw an ganged CMOS NOR gate. It is nothing but basically an inverter and another inverter okay, why it become a straight line. Okay, so two inputs, say A and B, and this is the output, and it is connected to how much? 4C, and the widths are given as PMOS is 2 by 3 and MOS is 4 by 3, 2 by 3, 4 by 3. Okay, I have to find the average logical effort. Okay, before finding that, let us look what will be my outputs for all the four combinations, input combinations. Okay, this is y, and this should let me write it is the current. Okay, so when A equals to 0, B equals to 0, these two transistors would be off, these two transistors would be on. Okay, and what would be the currents? The currents would be, it would be as it is 2 by 3, my current would be I by 3, I by 3. So it would be 1, and current would be, net pull up current would be 2I by 3, I by 3 plus I by 3, because both the PMOS would be conducting. We'll be pulling up the output capacitance to a voltage VDD. Okay, and when A equals to 0, B equals to 1, so this would be again on, this would be off, this would be, sorry, this would be off, this would be on. Okay, so this would pull down the output capacitance by a current of 4I by 3, and this would try to pull up the current by a current of I by 3. So my net current would be 4I, so output would become 1 because pull down strength is more, and net current would be 4I by 3 minus I by 3 equals to I should write it more clearly, by 3 plus I by 3 to 2I by 3. Clear, everyone, what is happening here? Similarly, for A equals to 1 and B equals to 0, Okay, a equals to 1, b equals to 0. This would be on, this would be off, this would be off, this would be on. Same thing will happen. The current would be, it will try to pull up by a current I by 3, and it would try to pull down by current 4I by 3. So I'll get the net output as low, and the net current would be 4I by 3 minus I by 3, that is I. Okay. And for the final case, when A equals to 1 and B equals to 1, okay, so this would be not conducting, this would be conducting, this would also not conduct, and this would conduct, right? So I'll get a net output of 1, and the net current would be 4I by 3 plus 4I by 3. Sorry, I'll get a net output of 0, because both are discharging this output load capacitance of 4C. Okay, this is also discharging, this is also discharging, and my net current would be 4I by 3 plus 4I by 3, that is 8I by 3. Is this much clear to everyone? I want everyone like to have clear idea about these currents and the outputs, how I am getting it. Is it clear to everyone? Okay, okay, fine. Okay, so now I want to find the uh, average logical effort. So for pull up, I only have one condition, right? I only have this condition, and I got this corresponding current. But for pull down, I got three conditions. So for finding the logical effort, if you remember, I have to consider the case where the current is least. Okay, that is the worst case. The current is least, and the current is least for these two conditions. So I can take any one of them. So let's first look into the pull up logical effort. As current is 2I by 3, I have to draw my reference CMOS inverter in such a way that I get a current of 2 by 3. So as the current is 2 by 3, my NMOS width would be 2 by 3, and my PMOS width would be double of that, so 4 by 3. Therefore, my G pull up would be how much? Now the capacitance connected here is how much? 4 by 3 plus 2 by 3 is basically 6 by 3, that is 2. Okay, so would be the pull up would be 2 by 3 is connected here plus 4 by 3. So 2 by 3 of this, 2 by 3 of this, and 4 by 3 of this and 2 by 3 of this. So it would be 2 by 3 plus 4 by 3 divided by how much? Divided by, I just found 2. How 2 is coming? 2 is coming from basically this one, 4 by 3 plus 2 by 3. So it is 2. So it's how much it is coming? It is coming 2 by 2. It is coming as 1. So pull up logical effort is 1. That is, it is pulling up as same strength as an unit inverter. And if I look at the pull down logical effort, for pull down of logical effort, let us first look into the reference CMOS inverter. The current is I. So my reference CMOS inverter would be our known CMOS inverter. NMOS strength is 1, PMOS strength is 2. The capacitance connected here is then 3C basically. Therefore G pull down would be 2 by 3 plus 4 by 3, this term, divided by 3. So it would be coming 2 by 3, because numerator will be 2, denominator is 3, so 2 by 3. And therefore my G average would be basically the average of pull up and average of pull up and pull down. So basically it's 1 plus 2 by 3 whole by 2. How much it is coming? 5 by 6. Do I have an answer of 5 by 6? Yes, I have 5 by 6. So this is how I am getting the average logical effort of 5 by 6 for a ganged CMOS NOR gate with given strength. Okay, so if anyone asks you about any other gang CMOS circuit, the approach would be similar. You have to find the output logics and the corresponding current, find the minimum current for different input combinations, draw your reference CMOS inverter, and then find the pull up and pull down logical efforts and get the average of these two pull up and pull down logical efforts as the average logical effort. Is it clear to everyone? Okay, so with this our today's previous year's assignment question ends. So if you guys have any question regarding this 10 questions that I have discussed today, you can go forward and ask me. Yes. Okay. Okay, let me draw what you are mentioned. Okay, we are doing an asymmetric gate. Say I'm having an inverter. So I say I'm having a NOT gate, NAND gate. Okay. Right. What is your question? Okay. 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 Why we are taking it? See, when does this NMOS circuit will come into effect? When does this pull down circuit will come into effect? When my output capacitance is already charged to some value and my NMOS circuit is trying to discharge it, right? This is what my pull down network is doing. It is discharging it. If it is already zero, then there is no point in discharging it. The current will be my this VDS would be zero, then 0 minus 0. So my net current would be 0. So there is no point in discussing it, right? That's why we discuss the case when uh, my output Y is already charged to value VDD. So my VDS becomes how much? VDD minus 0. That is, so I'll get some finite IDS current. Okay. And why you are asking why we are taking A equals to VDD? Because it's an NMOS transistor, right? So we have to apply, like in digital circuits generally we have two voltage levels, 0 and VDD, and uh, you provide any voltage here greater than VT, your NMOS transistor would start conducting. Okay, because NMOS is what? NMOS is strong zero, right? Strong zero or strong 1 p, strong zero. Okay, so NMOS will be able to discharge it completely to up to ground. So that's why we are using VDD at input and VDD as the as our what to say, as our drain voltage, because it is the output capacitance voltage that we are trying to discharge. And if I consider zero, like there is no point in discussing it. It is already discharged. What is the use of my pull down network? Did you get my? I can take any other value. I can take VDD by 2, then my circuit will basically discharge it from VDD by 2 to ground. And whether my NMOS would be in like in saturation or linear region would depend upon the voltages that I have taken at ground, at VG and VD. VG is already grounded. We can take any voltage. See, when we are designing digital circuits, we only generally work with two voltages, low level and high level. Low level is generally ground, high level is generally some voltage VDD. What is this VDD? It varies from technology to technology. Okay, it can be 2 volt, it can be 1.5 volt, it can be 0.7 volt, 0.8 volt. Okay, and we ensure that whenever an operation has been performed, my output reaches either VDD or 0. Okay, and using CMOS logic, we will see my output will reach one of the, it is called rail, these two are called rail, and this is called rail to rail swing, the difference between them. Okay, so I ensure my circuit does rail to rail swing, either it reaches VDD or it reaches ground. That's why while doing this and all these calculations we are showing from VDD only. But in, like, I again come back to memory, right? In memory also sometimes we don't charge it to VDD, we charge it to VDD by 2. Why we charge it to VDD by 2? Sometimes there are something called as sense amps present. Okay, there are something called sense amps. So what does sense amps do? If the current is low, if the current is low, then it changes the output to this low voltage. Okay, and if the current is high, it changes the output to high voltage. Now the initial voltage, if it was say kept 0, the time taken to reach this output voltage would be higher. Or if my time to reach this output voltage would be say x. Okay, and if my initial voltage was high, again to the time taken to reach this voltage would be again x. But if I use a voltage which is equals to VDD by 2, I can reach this rail to rail swing in half the time, say x by 2. So my circuit will become much faster. So it is not like that we always use this VDD. Sometimes in some of digital applications also we go to other voltages VDD by 2. And if you go to analog circuits, then though you will find many applications of different voltages, like in ADC or DSC or many other, any other, like in phase lock loops. There are multiple circuits, and we'll be using with all the whole spectrum of voltages, and how to get these voltages, how to generate these voltages on chip, and what will happen if these voltages are we encounter such voltages, or how to deal with them. Like there are lots of analysis in analog domain, but in digital domain we basically work with these two voltages only, VDD and ground. Okay, is it clear? What And the same logic holds for taking VDD at input. If I want to take VDD by 2 at input, if my VDD by 2 is greater than VT, still I will get discharging current, but my VGS minus VT term will decrease, right? My VGS minus VT term would decrease if I take VG as VDD by 2. So my discharging current IDS would reduce. So my delay would increase, right? My delay would increase. So as generally it is considered VDD is the highest voltage that can be used in the circuit safely. So we generally try to apply VDD at both at the gate terminal, and due to this rail to rail swing I get the output either as 0 or VDD. But like as I said, for analog circuits I can work with other voltages also, but for digital circuits we work with VDD and ground only. Okay, okay, give me a minute. Okay, question. Okay, R is equals to 10 kilo ohm. Okay, femtofarad. Okay, okay, 4:2, fine. Okay, 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 fine. So generally the formula was 12 RCN if I remember correctly. Okay, and from where this 12 RCN was coming, there was like propagation delay rise plus propagation delay fall, if I remember correctly. This was my net propagation delay. Yes, now tell me what is the confusion. Oh, I think I did it in the previous class also. I did the same question. You can go and check it. But let me do it for you. 12 R into C, and like what it is said, that there is an inverter and there are 11 such inverters after it. So total 12 inverters. or just total number of inverters is 11? What is the question? Parallel, it is mentioned. Okay, okay, fine. Like this, these are also different sizes, you are saying? Okay. You have to use this one. You have to use this one, rising delay and falling delay. Okay. And you have, what is propagation delay? I am telling again and again, it is the worst case delay, right? So here I think all the inverters, what they will be doing, uh, I think they all are being driven at the same time, right? So I think you need to consider, as your current will be sum of all these currents. So just look into it. I think the net current would be the, for pull up and pull down also, the net current would be sum of all these individual currents that are coming, right? So accordingly, mm, George, accordingly your propagation delay would change for this stage. Okay. And your net propagation delay would vary. It will not be simple 12 hours. It will not come with this formula. Okay, because here n is 2, simply 2. But as these are of different sizes, you have to solve it to find the value. You have to take same current, and this current would, I hope some capacitance has been given here. See, is any capacitance given? No, 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 no need of capacitance. I think it would be connected like this, right? It is an oscillator, right? Like, was the question about oscillator? Okay, okay, okay. I have to look into the question, but if you want to approach it, see, worst case, do one thing. I think what will happen, as it is not an oscillator, like this output is connected to all the 12 11 transistor at once. Was that the question? They are connected together. Okay, this one. Okay, okay. See, my approach would be, find the currents, and as all the net current with sum of all the currents. So basically your propagation delay would reduce. Okay, whatever propagation delay you would have got for single inverter, for 11 inverters, as your currents are in sync with each other of all the 11 transistor, your net current would increase, and hence your net propagation delay would reduce. How much it will reduce, you have to solve it. You have to find the individual capacitances, and then you have to solve and find the value, and then you will be getting your the whole circuits propagation delay, rise and fall. You have to do it for rise and both fall. I don't think so. I don't think so. I think you have to find the, like, you, as all the inverters are working in are in same state, right? If they are charging, they are all charging. If they are discharging, they are all discharging, because they have similar size and they have similar inputs, right? So instead of thinking, say, 2 is to 1, 2 is to 1, instead of thinking it like this, I can think it as 4 is to 1. Okay, understand my point? So use such kind of logic, and then find the net current, and then try to find the propagation delay from there. Okay, you have to handle it a little with little intelligence, because basically uh, they are connected in parallel means what? Your PMOS, if see, if during pull up, if it was 2, if it was 2 and it is 2, now both are pulling it up, right? Both are pulling it up. So basically it is acting as a single transistor with the 4, right? So use this logic to solve this one. 8 into 11 into 4 into 11, yes, correct. Okay, okay, fine. Yes. Okay. 2 is to 1. Okay, here you are talking about, see, see, okay, okay, I got it. See, if you are trying to find the current, PMOS and MOS. See, here the currents are equal. The pull up and pull down currents are equal. Okay, let me call this I1. Here again, this pull up and pull down current are equal, and let me call it I2. But is I1 and I2 equal? No, right? Got my point? But in case of delay, when you will be finding the RC delay, the interesting thing is, here my, see, if it was my R1 and it is my R2, my R2 is less than R1. Okay, my R2, see, my initial RC was R1 C1. Okay, and final RC is R2 C2. Okay, so what has happened, my R2 has reduced. Say I have increased the W by a factor of 2, so my R2 has become R1 by 2. Okay, but what has happened to my C2? C2 has increased, it has become 2C1, so it still has remained R1C1. So R2C2 equals to R1C1. That is, therefore, RC initial equals to RC final. With scaling, my delay remains equal. Okay, so in terms of delay, if I talk about, about scaling has no effect on delay. But if you are asking about current, whether current will remain same or not, current will not remain same, but delay will remain same. So this is the answer to your question. Then it is fine. Okay. Okay. Anyone, anything else? Harish, Nazma, Netra, Uthra, anyone, any question? Yes. Okay. 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 You are saying that if you take 8 is to 4 and 4 is to 2, you are not getting the desired answer. Okay. Okay, why you are not getting the desired answer is uh, propagation delay. Okay. How you have found the propagation delay? No, 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 no. 1 by 12 RCN was for oscillator, right? Don't substitute it here. I thought first initially it is of an oscillator. That's why I have written 1 by 12 RCN. It is not 1 by 12 RCN. It is for an oscillator, right? You have to find it manually. You have to solve it, either linear model or Almodile model. You have to find it from there. Okay. Anything else? Yes. And also remember, if you are using 2 is to 1 instead of 4 is to 2, I don't know, will this parasitic delay term come into picture? If parasitic delay terms comes into picture, you cannot take 2 is to 1. And if you are not encountering this parasitic delay term, then working with 4 is to 2 is fine. Okay. Okay, yes. Yeah. But you, actually you have to like when you'll be finding this propagation delay, I think it was that optimization problem, that where I have to find this g1 f1 such kind of thing. I think I have to do, like, I have to look into it, but I think it is f1 g1, you have to find it individually. If you are doing that, then parasitic delay terms will come into picture, because there was one term where you have to add the sigma of pi, right? If these things comes into then picture, then don't take 2 is to 1, because parasitic delay would be different. What happens with scaling, basically, see, in delay how many terms we have? We have one term of sigma pi, and we have something as n into f to the power 1 by n, correct? So if we scale our design, this sigma pi keeps on increasing, but this thing keeps on reducing. Okay, so that's why. And as it is a constant term, we don't care about it, and as it is reducing, we are interested in it. But remember that this thing is still present, right? So you cannot simply if you are considering this, then you can work with scaling. You can take 2 is to 1 also, but due to this sigma pi term, you cannot consider a 4 is to 2 inverter and 2 is to 1 inverter same, because the pi for 2 is to 1 would be how much? 1, and for 4 is to 2 it would be 2. So this pi would change, so you will get a deviation in the result. Okay. Okay, fine. Anything else? Yes. Okay. 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 So I think I have solved a similar question in the previous class also. Here you have been given f, you have been given. Okay. See, so this is the circuit. Okay, this is your current circuit, and this is the final circuit that you want. If you remember, I did a similar question in the last class also. Okay, so f value, you know, it was n1 was 6 initially. Now it is how much? It is capital N, let's talk, and it is n minus 6. Okay, so what is the net delay here? Net delay is n f to the power 1 by n plus okay, so n1 is 6 into this p, that is parasitic delay term, plus n minus 6 into inverters is there, so g is 1. Okay, and you have to do this with respect to n, and then you will be you will equate it to 0, and then you will be this f by n, you will be substituting with any variable, say x or y. I think I have used rho in the previous class, and then you'll be solving for rho numerical analysis through numerical analysis, and you will be finding the f to the power 1 by n. Then you will be finding the new values, that from that you can find the new values of n and n bar. then you can find the all the values. Sorry, from here you can find the value of n, the new number of inverters. It was the approach. If you remember, you can go and check the videos in the YouTube. Okay, it is easy, right? Because you have been given f. So if you know f, you know n, and you just need to see in these questions, you just need to draw the circuit properly. If you are able to draw the circuit properly, and if you are able to size it properly, almost any question you can handle it, you can face any problem. Okay. Okay, so if there is any no more further question, we can end today's session. Sure. I don't know. I have no idea. See, before final exam, I think you will have one live session with sir. Okay, so you can ask these questions to him. Like, but generally it will be MCQ because thousands of students are appearing for it. So it would not be feasible for the TAs to check all the, or for sir to check all the copies. So it will be MCQ only. Okay. Okay. Most welcome. So we can end today's session, everyone. Okay. Hope you guys enjoyed it. So then see you next week. See you. Bye. Goodbye, everyone.